Get this, a brand new research paper is saying that something called normalization layers in AI might not actually be as essential as everyone thought.
Hmm.
Neural networks, the brains of AI. Well, these normalization layers are kind of like the traffic cops inside, making sure that the data is flowing smoothly.
Yeah.
But what if we could just ditch the traffic cops and everything would still run smoothly?
That would be
That's what this research is saying. And they've even got a potential replacement, something called Dynamic Tanh or DYT.
It is pretty fascinating.
Oh, cool.
Yeah, this research really dives deep into how those traffic cops, especially the layer normalization type, were actually working.
Yeah.
They visualized what was happening to the data, and the results were surprising.
I love it when we can actually peek inside the black box of AI.
Right.
So what did they find? Did the data just flow in straight lines like a well-organized highway?
Not quite.
Okay.
They found these really distinct S-shaped curves, almost like a mathematical function called Tanh. And it's unexpected because normalization is supposed to keep things kind of balanced and linear, not create these curvy transformations.
So it's more like a winding mountain road than a straight highway.
Yeah, you could say that.
Okay, but why is that a problem?
Well, it turns out that those curves are actually doing something really important. They're squashing extreme values.
Okay.
Think of it like a bouncer at a club, keeping things from getting too wild.
Okay.
Those extreme values can really mess up the learning process, making the AI unstable and harder to train.
Okay, so normalization is kind of like a data bouncer.
Yeah.
But it's doing it in this curvy, non-linear way, and this new DYT thing is supposed to replace that.
Right.
I'm curious, how did they even come up with that idea?
Well, they took inspiration from what they observed. Remember that S-shaped curve?
Yeah.
Well, the tan function creates a very similar shape.
Right.
So DYT uses tan to mimic what those normalization layers were already doing, but in a much simpler way.
So it's like they discovered the AI was already kind of doing a Tanh dance, even though no one told it to, and they just decided to go with it.
Exactly.
Wow.
The formula for DYT is surprisingly simple. It's DYT of x equals gamma times tan of alpha x plus beta.
Okay.
The alpha is the real star here. It dynamically scales the input, so it's basically controlling how much squashing the tan function does.
So it's like an auto-adjusting squish factor, just making sure those extreme values don't get out of hand.
Precisely. And the best part is, DYT isn't another normalization layer.
Okay.
It works on each data point individually, like having a mini bouncer at every entrance to the club.
Right.
Instead of just one at the main door.
Okay, that makes sense. It sounds way more efficient than having one bouncer trying to manage a whole crowd.
Right.
But does it actually work?
Yeah.
Can something this simple really replace those complex normalization layers that everybody thought were essential?
That's what's remarkable. The researchers tested DYT on a ton of different AI tasks, from image recognition to language models, even DNA sequence modeling.
Wow.
And across all these different areas, DYT consistently matched or even outperformed models using traditional normalization layers.
Wait, so they're telling us we could potentially build AI that's just as good, if not better, but without all the complexity of normalization layers.
Potentially, yeah.
What kind of results are we talking about here?
Well, let's take image generation, for example.
Yeah.
Those AI systems that create incredibly realistic images.
Yeah.
Well, with DYT, they achieved comparable or even better image quality compared to the original models using normalization.
So not only could DYT make AI faster and more efficient, but it might even make AI-generated art even better.
Yeah.
That's huge.
They also tested DYT on massive language models like Lemma.
Okay.
And the results were just as promising. DYT achieved similar performance and training loss compared to RMS norm, the standard normalization that they use for those models.
Hold on. So they're saying we could potentially train these giant language models faster and more efficiently with this simple DYT operation?
Potentially.
Yeah. Imagine the possibilities, we could develop more sophisticated chatbots, build even more powerful language translation tools all in a fraction of the time.
Yeah, the efficiency gains observed with DYT, especially in language model training, were pretty impressive.
This is seriously impressive, but I have to ask, how does it work? What's the secret sauce behind DYT's success?
Remember that alpha parameter?
Yeah, the auto-adjusting squish factor.
Right. Well, it turns out that during training, alpha actually learns to approximate the inverse of the standard deviation of the incoming data.
So it's not just randomly adjusting itself.
Right.
It's actually learning something about the data.
It is.
It's like it has a little built-in data analyst, constantly monitoring the flow, making sure everything stays balanced.
That's a great way to put it.
Wow.
It's this dynamic learning ability that allows DYT to achieve similar results to normalization without all the complex calculations.
Yeah. This finding about alpha could be a game changer for anyone working with AI, especially as models get bigger and bigger.
Yeah.
But here's something that seems a bit counterintuitive, though. If alpha is like a control knob, wouldn't you need a bigger knob for a bigger model?
That's a great question. And it is one of the more intriguing findings of the paper.
Hmm.
They discovered that larger AI models actually seem to need smaller initial values of alpha.
Really?
Yeah.
That's like saying a bigger engine needs less fuel to start.
Yeah. It is kind of counterintuitive.
It's fascinating, but also a bit perplexing. Why would that be the case?
Well, it's not entirely clear yet, but it suggests that there's a lot more we need to learn about the dynamics of these large AI models.
This is all so mind-blowing, but before we dive deeper, I think it's time for like a quick recap. We've covered a lot of ground here, and I want to make sure we're all on the same page.
Sure. That sounds good.
All right, so we started by talking about normalization layers. Those traffic cops inside AI models that
Yes.
everyone thought were so essential. Then we learn that these layers, especially layer normalization, were actually doing something really unexpected. They were creating these S-shaped curves in the data flow, which turned out to be really important for squashing those extreme values.
Right.
And then we met like the star of the show, Dynamic Tanh, or DYT.
Yeah.
This surprisingly simple operation that mimics that squashing behavior using the Tanh function and this dynamically adjusting scaling factor alpha.
Right.
And the amazing part is that DYT seems to work just as well, if not better, than those complex normalization layers.
Yeah.
Potentially making AI faster, more efficient, and even better at certain tasks.
Uh-huh.
We also learned that alpha isn't just like some random knob.
Right.
It's actually learning to approximate the inverse of the standard deviation of the data, acting like a mini data analyst, keeping everything in check.
It is.
And to top it all off, we discovered that larger models might actually need smaller initial values of alpha.
Yeah.
Which raises some really interesting questions about the inner workings of these massive AI systems.
It does.
Wow, we've covered a lot of ground, but this is just the beginning of our deep dive. There's still much more to explore.
Definitely.
I'm already hooked. This DYT thing is like a magic trick, and I can't wait to see what other rabbits they pull out of the hat. But before we get ahead of ourselves, let's take a closer look at those tests they ran.
Okay.
They mentioned a bunch of different AI tasks, but I'm particularly interested in those language models and image generation experiments.
Yeah.
What exactly did they find?
So let's start with the language models.
Okay.
Remember those massive Lano models we talked about earlier?
Yeah.
They're used for everything from chatbots to translation tools. Well, the researchers decided to pit DYT against RMS norm, the reigning champion of normalization in those models.
So it's like a heavyweight boxing match, but for AI algorithms?
Yeah, you could say that.
So who won?
Well, it wasn't a knockout, but DYT definitely held its own.
Okay.
They tested DYT with a range of Llama models, including the 7B version, which has a whopping 7 billion parameters.
7 billion parameters.
Yeah,
It's mind-boggling how complex these models are getting.
it is.
So how did DYT handle all that data?
Well, impressively.
Okay.
They looked at both inference time, which is how quickly the model can generate text,
Right.
and training time, which is how long it takes to teach the model, and the results were remarkable.
Okay, I'm on the edge of my seat here. Give me the numbers.
Well, for inference, they found that using DYT instead of RMS norm significantly reduced the time it took to process the data and generate text. We're talking a reduction of over 50%.
Wow, that's cutting the processing time in half.
Yeah.
Imagine what that could mean for those chatbots we were talking about earlier.
Right.
Instead of waiting for ages for a response, you could have a real-time conversation with an AI that feels as natural as talking to a human.
Exactly. And faster inference also means lower costs, which could make these AI technologies more accessible to a wider range of people and businesses.
This is really exciting, but what about training time? Did
Yeah.
DYT also make a difference there?
It did. Remember, training involves feeding massive amounts of data to the model so it can learn and improve. This can take days, weeks, or even months for those massive language models.
Right.
But with DYT, they observed a reduction of over 40% in the time spent processing those layers compared to RMS norms.
So we could potentially train these massive language models in a fraction of the time.
Yeah.
That's a game changer for AI research and development. Imagine being able to experiment with new ideas, develop new applications, and push the boundaries of what's possible with AI at a much faster pace.
The possibilities are pretty exciting. Faster training means lower costs, faster innovation, and potentially even more groundbreaking discoveries in the field of AI.
Okay, I'm convinced DYT is a rock star when it comes to language models, but what about those image generation experiments? You mentioned that DYT achieved comparable or even better image quality, but I'm curious about the details. What kind of models were they using, and what exactly were they measuring?
They focused on a type of model called diffusion transformers, which are becoming increasingly popular for generating high-quality images. These models work by gradually adding noise to an image and then learning to reverse the process, essentially denoising the image to create something new.
So it's like starting with a blurry picture and then slowly bringing it into focus, but instead of a camera lens, it's an AI algorithm doing the focusing.
Exactly, and the key metric they use to evaluate image quality is called the Fréchet inception distance, or FID for short.
Okay.
It's a bit technical, but basically it measures how similar the generated images are to real images.
So a lower FID score means the generated images are more realistic and convincing.
Exactly, and what they found was that using DYT instead of layer normalization actually led to comparable or even lower FID scores in many cases.
So not only did DYT work,
Right,
but it might even make AI-generated art even better.
potentially.
That's huge. Imagine the possibilities for artists, designers, even filmmakers.
Right.
They could use these AI tools to create stunningly realistic images and visual effects with unprecedented ease and speed.
The creative potential is definitely exciting, and it highlights the versatility of DYT.
Yeah.
It's not just a one-trick pony. It seems to be capable of handling a wide range of AI tasks with really impressive results.
Okay, I'm officially a DYT fan, but before we wrap up for today, I want to dive a little deeper into the mechanics of how this thing actually works.
Right.
We talked about the Tanh function and the scaling factor alpha, but how crucial are they really? Did the researchers try like any variations to see what would happen?
They did. They wanted to make sure they weren't just stumbling onto like a lucky coincidence.
Right.
So they conducted some really thorough ablation studies.
Okay.
Essentially, they tested what would happen if they tweaked or removed different parts of DYT.
I love it when researchers really dissect an idea like that. It's like taking apart a clock to see how all the gears and springs work together.
Yeah.
So what did they find?
Well, first they tried replacing the Tanh function with other similar functions like hard Tanh and sigmoid.
Okay.
These functions also have that squashing effect on extreme values. So they wanted to see if they could achieve similar results with a different heart for the operation.
So they swapped out the engine of the car to see if it would still run.
Exactly. And what they found was that the choice of squashing function does matter.
Okay.
While hard Tanh and sigmoid allowed for stable training Tanh, consistently performed the best.
Interesting. So there's something special about Tanh that makes it particularly well suited for this task.
It seemed, so the researchers speculated that it might be due to Tanh's smoothness and the fact that it's centered around 0, which could help with stability and optimization during training.
Okay, that makes sense. And what about that scaling factor alpha?
Yeah.
Did they try messing with that too?
They tested what would happen if they removed alpha altogether, essentially making it a fixed value instead of dynamically adjusting during training.
So like setting the thermostat to a constant temperature and seeing if the house still stays comfortable?
A perfect analogy.
Yeah.
And the results were clear. Removing alpha led to a really noticeable drop in performance across the board.
Okay, so that dynamic scaling is crucial for DYT to work its magic.
It seems so.
But why? What's so special about having alpha adjust itself during training?
Well, here's where it gets really intriguing. The researchers found that alpha actually learns to approximate the inverse of the standard deviation of the input data.
Wait, so it's not just randomly adjusting, it's
Right.
actually learning something about the data itself.
Exactly. It's like alpha is a student diligently studying the data and figuring out the best way to keep things in check.
That's incredible, and it highlights like the incredible learning capabilities of these AI models. Even something as simple as a scaling factor can evolve and adapt to the task at hand.
Yeah, it also reinforces the idea that DYT, despite its simplicity, is doing something fundamentally similar to normalization,
Right.
controlling the range and distribution of the data flowing through the model.
Okay. I'm officially convinced that DYT is more than just a lucky hack. It's a clever and surprisingly effective alternative to normalization. But how does it stack up against like other attempts to get rid of normalization layers? I'm sure this isn't the first time researchers have tried to simplify these models.
You're right, there have been other approaches, but they often come with trade-offs. For instance, some methods rely on very specific weight initialization schemes, which can limit their flexibility.
So they're like baking a cake with a pre-mixed batter. It might work, but you can't really customize it.
Exactly. Others involve complex weight normalization techniques that can actually add more computational overhead, kind of defeating the purpose of trying to simplify things.
It seems like DYT strikes a really nice balance, simple to implement, computationally efficient, and doesn't require any major architectural overhauls. It's like they found the sweet spot for AI simplification.
Yeah, I think that.
It's like they found the holy grail of AI simplification, a simple, effective, and versatile solution that could potentially change the way we build these systems.
It's definitely a significant step forward.
Yeah.
But as with any scientific discovery, there's always more to explore.
All right, that's it for part one of our deep dive into this groundbreaking research. Join us next time as we explore some of the practical implications and potential applications of Dynamic Tanh and ponder what this discovery might mean for the future of AI.
Welcome back to our deep dive into this fascinating world of AI without normalization.
I'm still buzzing from our last discussion. It's amazing to think how something as simple as DYT could potentially shake up the foundations of AI, you know?
Yeah, it's a great example of how scientific breakthroughs often come from challenging those long-held assumptions.
Mm.
And speaking of shaking things up, let's dig a little deeper into those efficiency gains we touched upon earlier.
Yep.
Those llama experiments really piqued my curiosity.
Yeah, those results were pretty mind-blowing. You know, a 50% reduction in inference time and over 40% faster training for those massive language models. That's got to have some serious real-world implications.
Yeah, let's imagine for a moment that you're using a voice assistant to translate like a complex technical document in real time.
Okay.
Well, with DYT, the AI could potentially process and translate that information twice as fast,
Wow.
making the whole experience much smoother and more natural.
It's like having a personal interpreter in your ear who can keep up with even the most rapid-fire technical jargon.
Right.
And think about the possibilities for things like live captioning or real-time transcription. DYT could make these technologies far more accessible and accurate.
Exactly. And faster training times mean we can develop and deploy new AI-powered features and applications much more quickly. It's like having a turbocharged development cycle for all things AI.
This is all incredibly exciting, but I'm curious to know more about how DYT compares to other attempts to ditch normalization layers. Surely researchers have tried this before, right?
You're absolutely right. There have been other approaches, but they often come with some significant drawbacks. Some rely on very specific weight initialization schemes, which can be quite limiting.
So it's like trying to bake a cake using only one type of flour. You know, it might work for some recipes, but you're severely limiting your options.
Precisely, other methods involve complex weight normalization techniques that can actually add more computational overhead,
Yeah.
which kind of defeats the purpose of trying to simplify things.
It seems like DYT strikes a really nice balance, simple to implement, computationally efficient, and doesn't require any major architectural overhauls. It's like they found the sweet spot for AI simplification.
And remember, DYT achieved all of this while still matching or even exceeding the performance of those more complex normalization layers. It's a testament to the power of elegance and simplicity in design.
Before we move on, I want to touch on one more thing about the mechanics of DYT.
Mm.
We've established that the dynamic scaling factor alpha is crucial for its success.
Right.
But I'm still a bit puzzled by the finding that larger models might actually need smaller initial values for alpha.
Yeah, it's definitely one of the more intriguing aspects of this research.
Mm.
And it highlights just how much we still don't know about these complex AI systems. One possible explanation is that larger models with their vast number of parameters might be more sensitive to initial conditions.
So it's like trying to balance a giant stack of blocks. You know, a small nudge at the bottom could cause the whole thing to topple over.
Exactly. In smaller models, a larger initial alpha might not have such a dramatic effect, but in those massive models, even a small initial squashing could ripple through the entire system and impact the learning process.
This suggests that there's like a delicate interplay between the size of the model and the optimal value of alpha. It's like finding the right balance point for a complex ecosystem.
And as we continue to develop even larger and more sophisticated AI models, understanding these nuances will become increasingly crucial. It's a reminder that while DYT is a significant step forward, there's still much more to explore and discover in this field.
Well, this has been an absolutely fascinating deep dive into the world of AI without normalization. I feel like we just scratched the surface of what's possible with DYT.
And remember, this research isn't just about ditching normalization layers. It's about challenging assumptions, exploring new possibilities, and finding simpler, more efficient ways to breed AI systems that can solve real-world problems.
But before we get too carried away with the potential of DYT, I think it's important to address like the elephant in the room. What are the potential downsides? Every new technology comes with its own set of challenges and risks. What are some things we should be cautious about as DYT gains traction?
That's a crucial point. I think one concern is that a laser focus on efficiency could inadvertently lead to a neglect of other vital aspects of AI development, such as transparency and robustness.
So it's like optimizing a car for speed without considering safety features. You might reach your destination faster, but at what cost?
Exactly. As we embrace these innovative techniques like DYT, we must ensure that we don't compromise other ethical and societal considerations in the pursuit of efficiency.
We need to be mindful of the potential for unintended consequences. For example, could there be unforeseen biases amplified by these more efficient models?
That's a valid concern. While DYT itself might not introduce new biases, it could potentially exacerbate existing ones if not carefully implemented and monitored.
So it's like giving a powerful tool to someone without proper training. We need to ensure that DYT is used responsibly and ethically with a focus on fairness and accountability.
Another potential challenge is the need for further research and validation. While the initial findings with DYT are promising, it's still a relatively new technique.
It's like discovering a new species of plant. We need to study its properties, understand its strengths and weaknesses, and explore its potential applications before we start cultivating it on a large scale.
Exactly. We need to explore how DYT performs in diverse contexts with different types of data and cross a broader spectrum of AI tasks to fully grasp its capabilities and limitations.
This is all incredibly exciting, but I also feel a sense of responsibility as we delve deeper into the potential of DYT. We need to proceed with caution and a critical eye, ensuring that we're building a future where AI benefits everyone.
Well said. And as we conclude this part of our deep dive, I want to emphasize that AI is a constantly evolving field. DYT is a remarkable discovery, but it's likely just one step in a long and winding journey of innovation.
It's like the invention of the wheel, a groundbreaking innovation that paved the way for countless other advancements in transportation.
Who knows what other revolutionary ideas are just waiting to be discovered? Perhaps there are even simpler and more elegant solutions than DYT that we haven't even imagined yet.
The future of AI is brimming with possibilities, and that's what makes it so incredibly captivating.
This deep dive has been a testament to the power of human ingenuity and the relentless pursuit of knowledge. Who would have thought that a simple mathematical operation could potentially reshape the landscape of AI?
It's a reminder that the most profound insights often emerge from the most unexpected places.
And as we conclude our exploration of DYT, I'm left with a sense of wonder and anticipation for what the future holds. What new breakthroughs await us in the world of AI? What other long-held assumptions are ripe for questioning?
And most importantly, how can we harness the power of AI to create a better and more equitable future for everyone?
These are the questions that will continue to drive our curiosity and fuel our exploration of this transformative technology. Thank you for joining us on this incredible journey of discovery.
And we hope you've gained a new appreciation for the complexity, ingenuity, and boundless potential of artificial intelligence. And until next time, keep those minds curious and those imaginations soaring. Welcome back to the Deep Dive. We've been on quite a journey exploring this new Dynamic Tanh operation, or DYT, and its potential to revolutionize AI.
Yeah, it's certainly been a fascinating exploration, uncovering how a seemingly simple tweak could lead to such significant improvements in efficiency and even performance in some cases.
Exactly. But let's shift gears for a moment and talk about what all of this means for the average person. How could DYT impact the AI that we use every day? I'm talking about things like those voice assistants. We all rely on the chatbots that are popping up everywhere, even AI-powered tools for things like image editing or music creation.
Well, think about those times you've asked your voice assistant a question, and it takes a few seconds to respond.
Right.
With DYT powering those language models, those responses could become almost instantaneous, leading to a much more natural and seamless interaction.
It's like having a conversation with a real person, but with the vast knowledge of an AI at your fingertips.
Exactly.
And what about those AI-powered art generators that are all the rage these days?
Yeah, DYT could make those tools even more powerful and accessible. Imagine creating photorealistic images or composing entire musical pieces with just a few prompts, all thanks to AI models running on DYT.
It's like having a creative partner who can bring your wildest ideas to life.
Right.
But let's not forget about the potential impact on scientific research. Could DYT accelerate discoveries in fields like medicine or climate modeling?
Absolutely. Imagine researchers being able to simulate complex biological processes or model climate change scenarios with unprecedented speed and accuracy, all thanks to more efficient AI models powered by DYT.
It's like giving scientists a superpowered magnifying glass, allowing them to see deeper into the mysteries of the universe.
Yeah.
But as we get excited about all these possibilities, I think it's important to acknowledge that we're still in the early stages of understanding DYT's full potential and implications.
Yeah, we need to continue researching and exploring how DYT performs in different contexts, with different types of data, and across a wider range of AI tasks.
It's like we've discovered a new element on the periodic table, and we're just beginning to experiment with its properties and potential applications.
Exactly. And as with any new scientific discovery, we need to proceed with caution and a critical eye.
Yeah.
We need to ensure that DYT is developed and deployed responsibly, addressing any potential risks or unintended consequences.
That's a crucial point. While efficiency is important, we can't sacrifice things like fairness, transparency, and accountability in the pursuit of faster AI.
Right. We need to make sure that DYT is used for good, to benefit society and advance our understanding of the world.
It's like we're holding this powerful new tool, and it's up to us to use it wisely and ethically.
That's a great analogy. And remember, AI is a constantly evolving field. DYT is a significant step forward, but it's likely just one piece of the puzzle. Who knows what other groundbreaking discoveries are just around the corner?
It's like we've just opened the first chapter of a thrilling new book, and we can't wait to see what happens next.
The future of AI is full of possibilities, and that's what makes it so incredibly exciting.
Well, I think that wraps up our deep dive into this remarkable new research on Dynamic Tanh. We've covered a lot of ground, from the technical details of how DYT works to its potential impact on everything from voice assistants to scientific discoveries.
It's been a fascinating journey, and I hope our listeners have gained a newfound appreciation for the power of simple ideas to revolutionize complex fields like AI.
I know I have. This deep dive has certainly sparked my curiosity and left me eager to see what the future holds for DYT and the ever-evolving world of artificial intelligence.
Thanks for joining us on this episode of The Deep Dive. Until next time, keep exploring, keep learning, and keep those minds curious.